Yo. No, it's online. Okay. And is it working? Uh-huh. Good. Good, 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 good. Is it alive? Yeah, it's alive. Okay. No, no, what happens here? It says 0 viewers. Okay, it's working. It's working, it's working, it's working. Yo, everything is working. I see. Okay. Just one sentence. Yesterday, I had the list of complex exam plan, and I have seen that I will ask you from additive manufacturing. We were short-circuiting the thing with Mr. Turek Adam, so it's okay.
Yeah, actually, I checked. I want to talk about this, but at the end of the lecture. So.
But it's okay. It's okay. No. Where is my chalk? Pencil 1, pencil 2, pencil 3. And let's try to have something. Okay. Yo, start. Welcome to everybody. What do you see here now is the fixed week lesson of drive techniques here at the Technical University of Budapest. And this is a special lesson for students that are not really expert in such domains. So that's why we get more or less some refreshing of basic information of these, of the mentioned topics. Last week we were talking about the two-stroke engines, and also in the week before maybe. And globally we were talking about internal combustion engines. And now, let's say we have finished with that, and we switch to a different kind of energy. We switched from the chemical energy, I restart. So, we switch from the internal combustion engines to the electric engines, electric systems. And for that, the basic question is the storage of the electric energy. This is a quite actual question. We have more than one ideas how to store materials that can provide electric energy, or how to store the energy itself. While in a fuel like gasoline or diesel oil, it's quite easy to put it in a, I don't know, in a given volume, and it will keep its energy content. With the electric energy, it's quite different. It's like let's say fuel is like the hamburger that you buy, and you keep it at a dry place, and it will keep its shape for infinity. While the electric energy, it will be disappearing like ice on the sun. So, some words about chemistry, if you remember, and some words about electrochemistry in this domain. So let's start. Basics of batteries. The first thing to mention is the so-called electrode potential that you have learned in chemistry maybe. What does it mean? It means the difference of the electric potential of a material regarding to a standard electrode. And this standard electrode is usually the hydrogen electrode. So potential difference of a given material regarding to a standard electrode. And this standard electrode is usually what we call is the hydrogen electrode. This is the H2 electrode. And how it happens, it's really easy. We get bulbs of H2 gas in water. We get also metallic electrode in water. And what do we check here? What we check is the production of ions. Water can be decomposed to hydrogen and oxygen. And meanwhile, there's a lot of ions inside the water, like H plus for certain short time, oxonium, if you have heard in chemistry maybe about that. And also you get plus minus, different kind of metallic ions. And then we can say that if we measure the quantity of ions formed, this is something which is proportional with the electronegativity. So more ions you get in the water, more there's a potential to make something on the electric side. And this thing, the electrode potential, is a material constant or material characteristic. Electrode potential. This is a material constant, let's say, not constant, characteristic. It's, I'm seeking for the word. It's a constant describing the material, let's say. Property, thank you, property. Material property. And as such, it depends on pressure and also on temperature. So the process of making ions in a liquid, it depends on how the temperature is inside the liquid or around, and also how the pressure is around the fluid. You can imagine you are boiling your sausage in water. If it's cold outside, you've got to put more energy for boiling. If it's really hot outside, you're in a desert, for example, you need really small quantity of energy to make the fluid boil. And as we measure the electric potential by computing or estimating the boil quantity, the bulbs or the ions inside, so for the speed of reaction, the heat is better, up to a certain limit, of course. Okay? So usually we get standard values to be able to compare for the pressure. It's 1 bar, so it's the atmospheric pressure, which is standard. And as you have learned in chemistry, temperature is 21 degrees Celsius. Okay, so we get the standard electric potential for a given material. And when we make a pair of two materials, then we get relative standard potential so one quantity is let's say U1 quantity regarding to hydrogen, the second is U2 quantity regarding to hydrogen, and we get a difference between U1 and U2. This will be a relative potential for the material. And then positive and negative poles can be identified. So positive and negative as pole in the electricity or in battery techniques, it's always a relative position. And this relative position is decided always how the two given material, the two chosen material pair behaves relative to each other. Okay, so it can happen that in a given type of battery, one material is a positive pole, and if you pair with a different material, it can be also a negative pole. It depends on how it's paired. Okay, so these are not absolute rules in such case. Yeah. So, and now about the storage of the electrical energy. Storage of the electrical energy, it's a huge science itself, and there are engineers that are specified in nothing else than the storage of the energy. In a nutshell, and for saying shortly, if we want to store the electrical energy in a chemical form inside a battery or inside directly easily reach the form, then we get two possibilities. We can store it in a battery in the form of electric hidden in chemical reaction, and we can also store it in a condenser as static charge. Okay, these are the two basic shapes of storing the electrical energy as electrical system, or as electrical in its original shape, or in its original form, sorry. And today I will try to talk about batteries more and condensers a bit less. Okay? Is it clear? Do you get the question? Not so far. Okay. No, so let's start with the batteries. Question. Do you know where the name is coming from? Why is it called battery? You know that this word is also used in military, in the army, for a group of guns and so on. Battery is the same like the word pile in French. And pile means in English stack. Because Alessandro Volta, the Italian guy who started to study with electrical energy storage and electrical energy as such, he made the first batteries using, I don't remember exactly. He had textile discs soaked with acid. Textile disc soaked with acid. Then he put it in a, I don't know, on a desk. He put on it a carbon disc, next textile disc in acid, one more carbon disc, and they made a kind of sandwich, which was quite tall. So it's a stack, let's say. Okay. It was a shape of stack, and the power was given by the cross section of the discs and the height, so number of discs as such. And the Italians, I don't know how they call it, but the French called it with ampere and coulomb. They was calling it pile, means a stack of thing, and it was translated to the English somehow by battery, meaning also something similar, a stack of things. Okay, and the word went back in the French by battery, so it's about the etymology of the things. So, what we use and what is the most important in this case, the battery types, basic battery types. And the first and most common is the lead acid battery. It's quite old, it goes back to the 1860s. It's a quite easy to make and in the same time quite powerful layout, construction. Then the negative electrode, minus electrode. This is pure lead, PEB in chemistry. And the positive electrode in the system is also lead, but not in pure form, but under the oxide form. It's lead dioxide, PbO2 in chemistry, if you remember. Pb being the lead, O being the oxygen, and under script 2 means that there are two oxygen with one lead atom in the system. From that, we get a cell tension around 2 volts. And how it is built, structure. You get a grid structure, so instead of the textile discs of Volta, we get here a grid in metal. And the grid in metal is made of lead. Metal grid from lead. It looks like a wafer, the gofri. So it's a grid. There are metallic parts, and you get holes among them. And in these holes, you get a kind of jelly that is put in, like jam in your cake or in your gopher. So you get inside that's the holes, you get a spongy lead material, which is the negative pole, and you can also have spongy dioxide of lead, PbO2. This is the positive pole. And you get one positive, one negative grid, one positive, one negative grid that you put next to each other, but they are not touching each other. There's a fluid that communicates the ions between the two kind of grid. And this fluid is called electrolyte. And this electrolyte, in this case, for the lead acid battery, it's an acid, namely sulfuric acid. Sulfuric acid. In chemistry, it was called H2SO4, if you remember. In high school, maybe. Luckily, it's not in the pure form, but it's diluted with water. Diluted to around 32 degrees with water. Okay, so it's not a pure acid. It's a solution of 32, I'm sorry, it's percentage, 32 mass percentage, weight percent. Okay? There is an old scale, which is the scale, the Baumé scale, which means the weight percentage, and it was 32 Baumé degree. That was the condensation, or the quantity of acid in the water. And this kind of structure is quite easy to make, because lead is quite easy to manufacture. Water you get almost everywhere, and sulfuric acid is quite also easy to manufacture. So even these days in the cars, the main battery are lead acid batteries. Normal internal combustion engine cars, for sure. And also in electric cars. Because in electric car, you don't have only the main driving battery, but also for your lights, your radio, and for your mobile phone connection, you need 12 volts. And for 12 volts, you get a traditionally lead acid battery. Small one for sure, but you have one. So it's still alive. How do we measure the charge? I'm seeking for the word how to make the state of charging. That's it. The state of charge. It's also called SOC in electric vehicles. State of charge. How is like the quantity of electricity available inside the battery. Is it full, is it flat? How we can measure. For lead acid batteries, it's quite easy. We measure U being the tension of the battery. We know that it's in the peak it's 2 volts more or less, and if it's less, proportionally we get less charge in the battery, in the case of lead acid batteries. But also, as we get a fluid electrolyte inside, the second way is the measuring the density rho of the electrolyte. So either we measure the tension or we measure the density of the electrolyte. And we know that the density changes depending on the state of charge. So we can say charge state we have something like 1.88 kilogram by liter, and we have the flat empty, we get 1.16 kilogram by liter. So maybe you have seen such things at battery shops. You get just a small chamber with a small floater inside, and the guy puts it in a battery cell. He pumps out a small quantity of electrolyte and watches if how the plunger is floating deep inside the fluid. And that's how he can measure the density of the electrolyte. In big batteries, it's quite practical. In smaller ones, usually you don't have enough fluid to make such measurement. Then in small battery cases, you measure just the tension. Okay. Remark. If flat, the battery can freeze. So as the fluid has just 32% of sulfuric acid, and it has at least 2/3 of water, if it's not charged, then it can just freeze with all the properties that you know about the freezing of water. So it will kill the grits, it will just break the grits, one uncomfortable property, and the second, it can break the housing of the battery. And why it's frozen? No problem. But when it starts to melt, then your acidic water goes a bit round. And you know how the steel parts of a vehicle behaves in presence of acid. That's why, for example, in Russia, or in Canada, or in Alaska, it happens that they make insulation, thermal insulation around batteries. It also happens in the very cold zones that they just put away the battery from the car and put it in the heated rooms for the night. And it happens also in the really cold regions that they just don't stop the engine for the whole night. So the vehicle is idling all night long. In Russia, I know that people are living in cold temperatures. That means -40, -50 in the night in degrees Celsius. And in such cases, you don't use diesel engine for sure, because the diesel oil will freeze. So just gasoline engines. And these engines either have got a heated garage. Heating, I mean heated from the -50 around up to -20, -10 inside. At -20, a normal gasoline engine can start without problem, with a good battery. So you need to heat the garage up from -50 till -10, yeah. So in Siberia, there are zones like that. When you are looking at Russian vehicles, they look strange, they are quite rough to handle, but the Russians have their reasons for building and designing such devices. Okay. And if you go to the north in Canada, again you will see the reasons for such things. So lead-acid battery is really easy to handle, easy to manufacture, but has got its sensitivity in this case. And one more thing is that, first remark, second remark, during charging or in hot weather, water leaves the electrolyte. So the water quantity decreases in the cell, in the battery. Not the acid quantity, just the water. Why? Because if you are charging, a small quantity of the charging current just decomposes the water and makes hydrogen and oxygen gas. So the water quantity decreases in the electrolyte. Or if it's really hot, you are in the desert, you are going there all day long. The engine compartment will have a temperature of, I don't know, 80, 90 degrees Celsius, which is quite close to the boiling temperature of water as such. And the electrolyte will just evaporate and go out. So the water will evaporate from the electrolyte. So in a lead battery, regular check of the electrolyte level is required. And whenever you see that the level is low, what do you add? Just water. Distilled water, cleaned water that contains no other ions or no metallic or other particles. And you pour it in the cells very carefully, not to spilling away the acid inside. And this is what you cannot avoid with a classic lead battery. So electrolyte level check and adding distilled water is regularly necessary. Okay? So this is one of the basic property of the lead acid battery. Usually when you are learning for your driving license, these things you have to learn. How to handle your battery. As well as you have to learn how to change wheels, so basic things. Okay, is it clear till now? I hope you have learned, you have had basic information on that, or you have heard about that. So I continue with the batteries. So usually properties we like lead acid battery because it's cheap. When I say cheap, it's really cheap. Lead, it was used in the human technology since a very long time. If you remember the Romans, were using lead for covering their water conducts, because it was a kind of metal that was easy to manufacture and form. And also this kind of battery is really simple. To manufacture. Why we don't like it? That's because it's heavy. As you know, lead is a heavy material. In the old coach building and carrossery building of cars and buses, lead was used for flattening out the surface errors in the sheet metal parts. You have a joining of two kinds of sheet metal around the wheel or in the tail of or in the back of the car. Usually the car makers were just pouring melted lead to make flat zones and hide the joining of metals. It was very, very nice and easy to manufacture, but it was considerably increasing the weight of the car. So it's heavy, and also it contains dangerous materials. I say poisons for the human body. Lead is known for making problems in the nervous system, as we have experiment from the Romance age. It just perturbs the development and functioning of the nervous system. And sulfuric acid is just a killing poison. So if you're working for the mafia, usually you can make disappear whole bodies, human bodies, dead bodies inside the sulfuric acid, and then you pour everything just in the canalization. It can happen. So Italian mafia does not only base wallies to put the rubbish in. You get huge volumic meters of space in a wally. They also are buying chemical plants where they manufacture sulfuric acid, and also they collect garbage. So money from everything. No, okay. So the basic problem was, or were, problems. They were the presence of fluid or liquid, maybe it's liquid, liquid sulfuric acid, A2SO4, and the need for electrolyte level check, and they led to different solutions to avoid the presence of the fluid and to avoid this electrolyte density variation. And the solutions are, first, you get the so-called oxygen recombination battery, where you get a closed case no hole in it. So the vapor or the oxygen gas and hydrogen gas cannot go out of the casing, but it's reorganizing inside. Okay, and this helps to keep the battery maintenance free. Let's say like this. And the second solution is what we called, what is the English word for that? It's the so-called jelly battery. I don't know what is the appropriate English word for that. I have learned it, but I have forgotten for the instant. So the principle is, what is the English name for that? I have forgotten. I will seek for the word. Let's call it a jelly battery, which is still a lead acid battery. But here, the acid is soaked up in silica gel. Silica gel being the small white thing that you find everywhere in your electric devices that is intended to absorb the humidity inside the packaging. And this ability to absorb humidity can be used here for absorbing the diluted sulfuric acid. So if you put such thing between your positive and negative electrodes, then it can work, let's say, regularly. So when you put the case of the battery in any position in the space, your acid will not go out. And these kinds of batteries you use in scooters, for example, the small black batteries, or also in the temporary energy storage for a computer or for any kind of solution when you need a temporary energy storage. So these things last long, and there is no danger of spilling away the sulfuric acid. And a similar thing is the so-called AGM battery, where AGM is a kind of technology name. Here, instead of using silica gel, you get a boron silica pillow. And again, between and below the lead grits. So here, instead of silica gel, you get a boron silica. It's a different chemical material. It's like a pillow. How to explain it? It's like you get your couscous with your sheep, and the couscous is the silica gel or the boron silica pillow, and you get the meat inside. It's just covering the whole lead material. Okay. And whenever you get the sauce, it's absorbed by this material. Okay. So again, it can have a completely closed casing, and you won't spill anywhere the electrolyte in case of any problem. Also, in this case, you may have different layouts of grid, because grid can be just a metal plate looking thing, but it can be also, for example, round up. And the AGM technology uses mostly the grids that are round up, the scroll, and you get battery that is composed mostly of scrolls, and you can see it outside of the casing, that there are scrolls and not rectangular flat grids inside. AGM battery is used mostly in military vehicles, I think, they are much more expensive than the simple lead batteries. I say that price is double or triple, but they last more time, much more time, much longer time, sorry. So. And one more thing for the lead battery, lead acid batteries, the failure method of batteries. It's as simple as the spongeous material falls off the grid, first thing. So you get either the spongeous lead or spongeous lead oxide that falls off the grid because of the vibrations of the car. You get shocks, you get the engine vibrating inside, you get the wheels bouncing anywhere, and one by one the small particles fall out of the grid. This is not the problem itself. The problem is that this fallen material accumulates below the grids, and after a certain time it makes a short circuit when there's enough falling material to join physically the positive and negative grids. So it's a short circuit on the cell and it kills the battery. Short circuit between positive and negative grids. It's a typical failure method of a classical lead acid battery in cars, for example. So note, if you get the same car and same battery, and in one car you go only on flat asphalt roads, on the second car you go always off-road in mountains and desert and so on, where there are stones and the car is always bouncing, then the battery will die sooner in bouncy environment than in a flat environment, usually. So remark, AGM prevents falling off. As if you get a pillow around the grids, the material just cannot fall off. So again, you get higher lifetime for that given kind of battery. And the chemical reason is also important. Formation of calcium sulfate, CaSO4, on the surface of grids. Sulfate of calcium is a material that also can be created from sulfuric acid if there is carbon dioxide in the air or carbon dioxide diluted in the electrolyte. And if you get internal combustion engine, for sure you will get a given quantity of carbon dioxide in the air, either from exhaust gases, from the fuel, evaporating fuel, from the oil, evaporating oil, from Carter gases. So for sure you will get a kind of, wait, what I'm talking about. Calcium. Sorry. I switch back. where you can get calcium in the battery. For sure, you will have a small opening breathing hole on the casing, and you will have dust in the air. And dust can be different kinds. Dust can contain silicon particles, dioxide of silicium, like sand, and also it can contain other particles, other kind of dust, like calcium carbonate, like calcar. And from that, if they fall in the acid, they transform a part of the acid to calcium sulfate, and this material is electrically inert. It avoids the electrical reaction, avoids the electricity to go out of the grid, and it covers the surface of the spongious material, and it kills the battery. Usually, if it's not the falling off of the spongious material, then this is the formation of calcium sulfate on the surface that kills the battery. And the battery lifetime, the practical experience is that it goes from 5 to 10 years. And usually after 10 years, the surface is covered by calcium sulfate from the dust of the air. Though there are practices to remove this by different chemical processes, it's quite expensive, and usually it's cheaper to just buy a new battery. Okay, if you get huge batteries for trucks or for other larger devices, you can try to remove the calcium layer by tricky processes, but it's not often possible. I have heard that in Hungary, in this country, there are special specialists in battery charging that can make chargers that goes current with impulses, peaks in the charging current. And these impulse in the charging current has got just one purpose: to break the calcium layer on the battery surface. And once the layer is a brittle layer, it can just fall off. And it can have a second life of the battery. Obviously not so high than the first one, but still something can happen. And if the insulating material falls off, no problem. It will still insulate, even if it's accumulated and joining the two grids. Okay? It's really, really tricky. No. Is it clear? So this is what we use in almost every road vehicle, every car, every truck. One kind of lead acid battery. And now comes a different kind of battery. A different kind of battery. Let's call it the nickel-cadmium battery. Ni is for nickel, Cd for cadmium. Nickel-cadmium battery. It was created or assembled not so long time ago in the 1960s. If you get the small round button-like batteries, these were initially the nickel-cadmium batteries. Here, the positive electrode is nickel, and the negative electrode is the Cd, being the cadmium. Both are metals. And how is it built? structure. Maybe you have heard about the nickel. Nickel is an additive and alloy for steel. And you want to make steel from the iron. You add different materials. One is the nickel. So it was quite common and well known in the material technology. Cadmium is a bit less practical because it's really toxic. But for making a battery, sometimes we use toxic materials. So structure of the battery is that you get sheet metal pairs. So you can just cut them away from a larger sheet metal. And you get the electrolyte, a special electrolyte inside. That is a crystal when charged, and a jelly when flat. So it changes its state, let's say. And that's why you can see that if your small button batteries are dead, you can observe the fluid going outside of the battery. While it's changed, it's completely dry, and you see no presence of fluid outside. Because it's more or less, it has crystal structure. Advantage, disadvantage, properties. We don't like the cadmium material. The cadmium is a strong poison. You get in all package, you get the message, do not eat. It's really a strong poison. There are stories on the internet everywhere that the little child has just eaten one battery like this, and it was just made a hole in his internal, what is the English name for that, esophagus? The tube which esophagus, yeah. The tube that goes to your stomach. It has a hole because of the acid content and the cadmium content, so it's very dangerous. The advantage, there are a lot of advantages. Small size, it's cheap, and also no sulfuric acid, no sulfuric acid inside. I don't know exactly which acid is inside, but for sure there's no sulfuric acid. So there's a lot of positive properties. That's why it's used in electrical devices that requires not too much power. So negative, it contains a strong poison. Positive, small size, cheap, and no sulfuric acid inside. And further properties. As every battery is, the capacity decreases when not used. So if you get this battery and you don't use it, so it will not only use its current or its internal electrical charge, but also the ability of carrying electricity will decrease. Okay? And it's a quite uncomfortable thing. And that's because the reason of that is that the size of crystal grains increases. In the electrolyte. So if you have this battery, you've got to move the interior constantly, either charge or discharge, but constantly, and then it will have a long lifetime and large capacity. If you don't touch it, you leave it at a given state, for sure it will decrease not only the electricity, the charge, but also the capacity. Okay? So it requires regular charge and discharge to keep the internal state at a healthy situation. And one more uncomfortable thing requires complete discharge before charging. So this was the case of the laptop batteries some years before. When you have read the user notice, or also for the mobile phones some years before, it was written, first charge it, then discharge it, then charge it only if it's completely flat. And it was told, if you charge it when it's just half flat, you will decrease the lifetime of your battery. Luckily, this is not the case today, but at the time when we were using nickel cadmium batteries in mobile phones and laptops, it was a serious problem. It's not so long, let's say it's 20 years ago. I remember such advices in the user manual, different devices.
But nowadays devices, for example, the laptops,
Yeah.
for the battery, let's say it's like 80% or 100% charge.
Yeah.
Is it recommended to put it on charge also?
So the question was, because it cannot be here held in the micro, the question was that what about the laptops batteries today? Can we charge it if it's just at 80% of charge and not less? I say first we have to read the user manual at least once. What's the indication? And if the structure is different, usually we have nickel metal, lithium ion batteries, a different kind of battery I will just talking about in some minutes. Then again, there's a different way of behavior. So first we have to identify what kind of battery we have in our device, and then we can see, depending on the battery type, how to handle that given type of battery. So unfortunately, there's no general rule for battery handling. There is one rule for lead acid battery, a second rule for nickel cadmium battery, a third rule for lithium metal ion batteries. So you've got to identify what's in your computer. Usually, in these days, you get lithium metal ion in your laptops that you can charge at every state of charge. But still, these batteries like to be flattened out before charging. But it's not an imperative condition that it has to be. It likes. And also, it doesn't like to be charged to the top and left unloaded for days. But it's a basic property of lithium-ion batteries. I will talk about. Okay? Good. Yes. Okay. And now just comes the next step of batteries. Next type, this is the nickel metal hybrid battery. Nickel metal hybrid battery. So what does it mean? It's more modern. It's the 1980s. Where the positive electrode is still the nickel, Ne, so nickel. And the negative electrode is some metallic alloy, some metal alloy containing hydrogen. So it can be more than one type of metallic alloy inside. And the tension here is around 1.25 volt by cell. And we can say that operation and use as same as nickel cadmium battery. In this case, you don't have the poisonous cadmium inside. You get some different metal alloy. And remark, charging is heat sensitive. So if charging is heat sensitive, you have to have a complicated charging algorithm required with temperature observation. So you need a complicated charging algorithm that watches the temperature while charging. Is it clear? So nickel cadmium, we don't have so much anymore, except in the small button batteries. And nickel metal hydride, it was very trendy in the, let's say, still 20, 30 years ago. They were the first generation of powerful batteries. For example, in the case of the digital cameras, the first digital cameras were using nickel metal hydride batteries. So this one. And I get special chargers at home for nickel metal with temperature sensor. Okay. And the third type that we use mostly today from the point of view of chemical composition. From the point of view of chemical composition, we get the third type. We get the so-called lithium-ion battery. Li being the lithium, if you remember, it's below the hydrogen in the left side of the periodical table of elements. Again, it's a metal, but quite special one, and it's quite lightweight, just the opposite of the lead, which is quite heavy. Here, the positive electrode this is not the lithium, this is just carbon, C, carbon. The negative electrode, again, this is not the lithium. It's a kind of metal oxide that can be pretty different kind. Dioxide of mangan, MnO2. It can be phosphate of iron, FePO4. So again, there is no lithium inside. Neither the positive or the negative. So where is the lithium inside? The lithium is in the electrolyte. Okay. So the electrolyte. This is where you find the lithium, namely lithium, phosphate, and fluoride, LiPF6, or lithium, boron, phosphate, LiBF4. So this is where we get the lithium. And usually the tension this is around 4 volt by cell, which is quite high. And this is a reason why we use such batteries, such cells in electric cars. Because you know from basic electrotechnics in physics that higher is the tension, less is the current. And in the wires that conduce the current, the resistance is proportional with the current size. Higher is the tension, you can pass more energy in a driven cross-section of wire. Okay? Nah. Good. And the very popular so-called lithium polymer batteries. What is the difference between lithium ion and lithium polymer? And the difference is that instead of any fluid or moving electrolyte, you get a thin polymer layer. So again, you get a cushion, a pillow between the positive and negative electrode materials, which is a polymer material. Maybe there is still the electrolyte inside in a solid or jelly form, more in solid form, but the basic material is a polymer layer. Okay. So for that, it's easy to form the cell. Okay. So while a classic lead acid battery is a large thing because you get cast parts in it, here you get metal layers, or you get a carbon, thin carbon film, plus you get a polymer layer. Inside you get the lithium electrolyte hidden, and on the other side you get a mangan oxide or iron phosphate layer. And it's like a sandwich, a flat sandwich. You can have a square one, you can have an enrolled one, you can have any shape you like to produce at the end. Okay? The advantage for lithium polymer batteries lithium itself is lightweight. It's not as light as hydrogen gas, but still among metals it has the less weight. So small weight. Also, it has no memory effect. So the capacity does not depends on the way of use. I explain. If you get a battery that is I don't know, in a pocket calculator, if you remember this thing, which consumes just a little current, but long time, and you get a battery that is in a hair dryer that requires high current for heating up the wires in a short time. There are batteries whose capacity adapts to the way of use, how you extract the electricity from the battery. And if you change two identical batteries from one device to another, the battery will remember how it was used, either for high current in short time or small current for a long time. And it's not the best. If you get a car, sometimes you drive shortly in a city, you go slowly. Other times you go outside the city on highway and you want to go longer distance and higher speed. If your battery is really formed and adapted to the local way, local traffic, it will not be good for going long. So these properties to avoid. And lithium polymer batteries have no this kind of effect. You have they have small internal resistance. So small self-discharge. What else? And small quantity of toxic materials. So it's all rows, it's better, no memory effect, small self-discharge ability, no toxic but But lithium, have you seen lithium in chemistry? Lithium, how is it stored? It's a classic experiment in chemistry. The lithium usually is stored inside a bottle of oil or petroleum, but more usually, or water, I don't know. Because lithium, if it gets in direct contact with the air, the oxygen, it starts to burning. It's a really unstable material. So negative properties, fire, danger. So if you are dealing with electric cars, the first problem, if you have an accident, is to check what about the batteries. Are they touched by the accident or not? If not, you are more or less happy. You can still have a high current electric shock, but you will not burn alive. Practically, in the dismantling guides of electric vehicles, it is told, and also there's a formation for the fireman, that if you go to accident where you get electric car concern, get the people out of the car as quick as possible, then go away. Because nothing can ensure that the car will not catch up fire by itself. And if it happens, you just leave it burn, or you have to use materials other than water. Because electricity and water, not friends, not friends. And for dismantling an electric car, very important to have a large, I don't know, swimming pool full of water. You put the electric car inside for some days so that it loses all the electric charge, but really all. And once it's short-circuited for days and have lost all the electric capacity, then you can start it to dismantle. At least the battery zone. These are silly things, but still. It is full of lithium. It's really, really dangerous for fire. Heats up during charging. So we have to watch it. We have to have a control electronics and active cooling. Required. It's really important to have a cooling of the batteries in your electric car. And not only cooling, but heating also. So it's really a paradoxon. The battery operates greatly in a given temperature range, namely between 0 degree or 5 degrees Celsius and 25 degrees Celsius. Below, you've got to heat it to operate, and above, you've got to cool it down to operate. So if you get electric car and you go to, I don't know, Finland, Norway, there's a lot of electric cars in Norway, or Sweden, in the north. A considerable amount of the energy stored in the battery goes for its own heating. And the opposite happens in the African countries or in the Near Orient, Far East. If you go to the desert and you switch on the climate because you don't want to die by overheating, a considerable amount of the cool air or water, it depends, will go for cooling the battery. It's very important. In early electric cars, there was some examples of no heating. in the first generation of Nissan Leaf, for example. There were no heating or no cooling because they were told, it's not important, let's hope. And the cars in Italy, we imagine a parking lot on the sunshine. Below you get the asphalt, black asphalt, sunshine outside, 35, 40 degree of temperature in the air, let's say 50 to 60 degree on the asphalt, and you get the car standing there for half day or 1 day. This was first case. It was just boiling out the water from the batteries. Or second case, when you start driving on such hot roads. So you get a working normal heat of the battery plus the heat from below. So don't buy first generation electric cars from Italy. This is the moral of the story. Okay, buy electric cars that have got a dedicated cooling for the battery. The heating is easier because you just put a small resistance and it heats up the inside. But the cooling is as important as the heating.
So even during the charging of the battery, we need to heat it up.
If there's cold out, the question was if you need a heating for charging, during the charging, yes. If it's cold outside, let's say below minus 5 degrees Celsius, you start the charging and most of the current goes for heating up the cells. And once the cells have reached their comfortable temperature, let's say around 10 degrees Celsius, then they can accept a stronger current. Below, they cannot. So in Canada, for example, if you get electric cars, either they are always plugged in to heat the battery when it's cold outside, or if it's cold outside and you have left the car unplugged, first you push your car inside your heated garage, you heat up the car up to, let's say, minus 5 degrees from minus 25 in Canada, southern Canada, and then you plug it in and you start the charge. There's opposite example also. You get the so-called solid state batteries. That is a quite early technology these days. They are operational, but operational at 60 to 70 degrees Celsius. So they have to heat it up to operate. And you had the Bolloré cars in Paris, France. And these cars were using their own energy to heat up the interior of the cells to 60, 70 degrees Celsius. So you get, when the car was switched off, you had, let's say, you had 1% of the capacity consumed by the heating of the cells. So it could provide you high power, but it consumed energy even when idling or not in use. While the lithium ions, they are not consuming energy when not used. Okay, so as you see, we get more than one kind of chemical layout, chemical structure of batteries these days. We don't know which will be the better, actually. In 5 years, maybe we have more experience. And every type of battery, from the chemical side or from the assembly technology and manufacturing technology, has its own specificities. Okay, it's very, very strange. Now, to finish with the properties of the lithium polymer, advantage we had it, disadvantage, fire danger, and yeah, one thing is the price in constant decrease. But still, it's quite high. So let's say you have a car that costs, I say a number, which number I say? Roughly. Let's say you get a car that costs 10 millions, a number. If you have your battery that's dead and you want to change it after 5 to 10 years, it costs you another 6 millions. So let's say 60% of the price for the early electric cars. Now let's say we are around 50% actually for electric cars. It's still high. And note that there's a general curve for battery capacity lifetime. And you can say as a thumb rule that you've got your brand new electric car with a large battery capacity. And the experience is that the capacity decreases 5% by year without doing nothing. So first, you can go away at a high speed at a given distance, let's say 100 kilometers you can make, or with a Tesla you can go from Budapest to Vienna on highway without problem at legal speeds. And then you charge it for one and a half hour on the supercharger. It depends on your battery and car. And in 5 years, you can still go from Budapest to Vienna, but a bit less than the legal speed. Let's say 70%. And the electric car knows perfectly the energetic. So either you go at long distance at a slower speed, or you go fast but at a shorter distance. It's a quite interesting experience. And for any case, the battery capacity is decreasing. The lifetime that they give to electric vehicles is more or less around 80% of capacity by 5 years. Okay? So it's good to compute. If you're delivering pizzas around the town, short stops, short distances, electric vehicle is perfect, any kind. If you are moving heavy freights between cities, diesel truck. Or if you are going in zones when there is no electricity, Canada, Russia. Again, internal combustion engine. Okay? In regions where you get more people and the cities are just like a pearls in a chain, then you can have your electric car. You get enough infrastructure to charging and so on. But there are zones, or if there's cold or there's very hot, the climate is very cold or very hot, electric car, not the best actually, not suitable for that. Okay, so I think we finish for today. And next week we continue with charging of batteries and other, I will see some words about fuel cells and some words about electric engines. Okay, and also next week we get a test. The 5 hours in the afternoon, was it okay for the test time? Like it was last week? Was it 2 weeks ago? Was it okay? Yeah. Okay. Then it will be the same next week. Do you have any question concerning this?
Thank you.
No questions. Okay, thank you very much for your attention. And then see you next week, and we continue from here. Bye.